general form of the quadratic function is any function from f of x ax squared plus bx plus c. For a, b, and c, real numbers. A is 2 equal to 0.
Not equal to 0. Yeah.
It is different from linear function because it contains squared graph. Any quadratic function is called graph. Shape graph comes up.
Okay, thank you. So let's just take a look at a couple of things that you may like overlook in this first paragraph. This form right here of the quadratic, ax squared plus bx plus c, this is the form you're used to seeing it in. You usually see it as y equals that, and often you set y equal to 0 when you're solving your quadratic for the values of x that make y 0. This is called another name for this is the polynomial form. This is the polynomial form of the equation. And a polynomial is just a bunch of terms. These are 3 terms, and your exponents are all non-negative integers, 0, 1, 2, 3. The polynomials, as you know, are nice in the sense that their domains are all real numbers. You don't have any trouble spots. So this is polynomial form. Of course, another name is general, because the general form of a straight line is not one you're used to seeing. Looks like this: ax plus by is c. So we use these letters a and b often. If you have a quadratic, you're going to need an a, a b, and a c. If you had a cubic, you'd need an a, a b, a c, and a d, and it goes on like that forever. So a is what we call the leading coefficient, because it's the number that multiplies your x squared term. It's the leading coefficient. B is called the linear coefficient because it would be, it's called linear because this term is x to the first power, which if we were just graphing something like bx, it would be a line. And this is called c, the constant term. Now, as we know, we may not have a term that has an x part, and we may not have an equation that has the c part, but we always have to have an equation that has a equal to some number other than 0, because if we didn't, then we would be looking at a straight line instead of a quadratic function. Okay, so that's polynomial form. What we're going to be working mainly with today is something called the standard form or the vertex form, which looks like this. Okay, notice this doesn't have 3 separate terms like up here, ax squared plus bx plus c. It has 2 terms. It has this term and it has this term. Okay, so there's going to be some real advantages to having this standard form, of what I call this, the vertex form, versus the polynomial form. So let's take a look at that. So most of you were working for a while on transforming our parent function right here, x squared, which is f, here's our picture of f, into this new function g. And we know that g tells us that we have a vertical stretch of 2 by a factor of 2. We have shift right 1 unit, and this tells us we're shifting down 1 unit. 3 units, thank you, 3 units. All right, so right away I can take my vertex, I can move to the right 1 and down 3, and this is now my new vertex. And I can do a similar thing with other points on this parabola. I can also just say I'm going to take each one of these points and I'm going to perform these 3 operations, these 3 transformations all at once. You can do them individually, but let's save a little time and just do them all at once. The first thing I'm going to do is my shape change, which is multiply all my y values by 2, which is going to make this 18. I'm going to shift my x value to the right 1. It's going to increase by 1, so this becomes negative 2, 18. And then my final thing is to drop all my y values by 3, shift down. So this is my 1 point I have. So if we do that with all of these points, we're going to have negative 2, negative 1. I move it to the right after I double it, and then let's drop it down 1. So there's my very first down 3. there's my very first point that I can plot here, negative 1, 5. And then this becomes 0, 2, and then it becomes 0, negative 1. Is that right? No. What did I do? Add 1, double that, add 1, and drop. 0, negative 1. Oh, I just plotted this point in the wrong spot. This point right here. That was my original vertex I was looking at. Okay. And then this one, I double 0, I get 0. I add 1, and then I drop it by 3. So it's 1, negative 3. This is my new vertex. Now that I have these 3 points, I can get 2 more points because I know that my parabola has symmetry around a vertical line. In this case, that vertical line goes right through the center of my new vertex right here, has the same x value as my vertex. So this line is x equals 1. So that means if I have a point that's 1 unit to the left of my vertex, 1 unit to the left means I'm on the y-axis here, means I have a point at exactly the same y value, 1 unit to the right. That's what symmetry does. So I can plot a point right there, and all of you should probably see 2, negative 1 on your sheets. And also this point, how far to the left is that point from my line? 2 units to the left, I'm 5 units above, so I can go 2 more units to the right, and I can be 5 units above there. So if you find a couple of points on one side of your line of symmetry, on one side of your vertex, you can immediately find their duplicates on the other side. Okay, so that's one quick way of graphing or sketching a parabola. Here we go. Okay. All right, so the new vertex is 1, negative 3. Most of you had that on your paper, okay? And so now the question is, if I have my quadratic function in this form, can I look at this and know quickly where the vertex of my new parabola is? And what did you say? Yeah. And how did you explain it? Yeah, anyone? Sure, go ahead. Yeah. Yeah.
Whatever is after the parentheses, so it's going to be -3, that's just going to be the
Okay. And the reason is because this is, you know, your movements from your transformations. This says you go, if you always imagine your parent function being at 0, this tells you go to the right one, there's your 1, go down 3, and there's your -3. It works just like all the work we've put into transformations for the last week or two helps you when you look at this. Okay. Now notice this form has a subtraction here. And the general form of this particular, the vertex form is always going to have a subtraction here. So if you're moving to the right, this number will be +1. If you move to the left, it will be negative, and that changes that to addition. So if, in other words, if I had something that looked like this, h of x equals 2 times x plus 1 square minus 4. If we want it to look like this form here, you would have to write this, 2 times x take away a -1. And that shows you that you've moved to the left 1 unit. And that's another way of seeing that you shift to the left 1 unit. If you make that a subtraction, you go left 1 unit. So the new vertex here would be -1, -4. All right. So this form comes in handy because when you look at this, you know a couple of things about your parabola. You can immediately identify your vertex, and you can also tell which way it opens. Because this number out here, this 2, is exactly the same as the 2 in this form up here. Let me show you that for a minute. You may not know that just from looking. So let's take away all of this. And let's convert this to polynomial form. So right now, this is what we call standard. Your book calls this standard form. Don't ask me where they got this name, but they call it standard form. I always refer to it as vertex because that makes sense to me because I can pluck out the vertex right away. But just so you know, when you're reading your book or you're looking at your homework, they call it standard form. How do we make this polynomial form? Well, just take your equation and do a little algebra. So you want to square your quantity x minus 1. So we're going to get x squared minus 2x plus 1 when we square that out. Subtract 3. Now we double everything. 2x squared minus 4x plus 2. Take away 3. And now we get 2x squared minus 4x. Take away 1. Okay, so this is equal to this polynomial form. And the one thing you should notice, and this is true for all parabolas and actually all polynomial functions we're going to look at in the future, the a value that's here, the leading coefficient here, is exactly the same as the leading coefficient here. So if you see this form right here, you can pluck off that 2 and put it right in there for a, because they'll always be identical, no matter which form of the equation you're looking at. This is the leading coefficient. It's exactly the same as the leading coefficient right there. Okay. Anything else I want to talk about here? Also notice in this form, in your polynomial form, just like with your straight line, your constant always tells you your y-intercept, right? With your straight line, we call that b because we only have 2 terms. This is c. There's your y-intercept right there. When x is 0, that disappears, and y is -1. So this form gives you some information that you can't get from this form. This form gives you information you can't get from that form. So depending on what you have to work with whatever information you can extract from the equation. All right. So when your a value is positive, you have a happy parabola, and it opens upward, which we're going to see in a minute down here. So when we have this form, the standard form, and a is positive, when you're a positive person, you tend to be happy, so your parabola opens upward. Now, I just heard this great talk by Dr. Ruth Potee, P-O-T-E-E. She's a physician in our community. Let me turn this off. All right, so if the coefficient in front of your parabola is positive, it's opening upward. If it's negative, it's opening downward. So as you can see up here with the one example, we have 2 as a positive number. This certainly opens upward. Our parent function has a 1 there. It opens upward. All right, what else do we want to talk about here? A is the leading coefficient. This form of your parabola, you can identify your vertex immediately from this form. That's why it's useful. If a an absolute value, because remember, a could be positive, negative. If it's a big number, whether it's opening up or opening down, then your parabola is going to become very narrow because it's being vertically stretched upward or downward. If a is a fraction between 0 and 1, an absolute value, then your parabola is becoming it's a vertical shrink, which is making it wider and wider. So look at this question here in your groups and tell me what you come up with. This thought question. I'll wait for a few minutes. So what do you think out there in algebra land? What's going to happen to this parabola as the coefficient for a gets closer and closer in absolute value to 0? What's going to happen to it? It gets wider and wider, so what's it going to approach? The x-axis, and what's the x-axis? Horizontal line, right. So let's take a look real quick. So here's x squared. Let's take a look at a small value of a out front, and let's say 1/2 x squared. So here we go, 0.5 times x squared, and let's see what happens. Invalid? What's invalid? Oh, I've got the equals. Yeah, that always helps, doesn't it? Okay, so it got wider. So let's even get smaller, like how about 1/10? Let's call this j of x equals 1/10 x squared. There you go. Let's move it over. It's getting wider and wider. And let's get even closer to 0. Let's say, how about 1/1000? All right, you want to do 1/100th first? Let's do 1/100th. Oh, let's do 1/100th, 0.01. Oh, I'm looking down here. Where am I, K of X now? Tell me if I type anything incorrectly here. Oh, 100th, yes, I do want another 0, thank you. There we go. All right, you think we're going to be able to see it if I put 1,000th in there? That's pretty close to, right? And depending on my yoga, oh, when you stretch, all right. Let's try 1/1000th. Let's see, L of X, 0.001 X square. Woo, look at that. You can barely see it, right? So yes, as X gets closer and as A gets closer and closer to 0, your parabola is getting wider and wider to eventually it would be at 0, it would be the x-axis. All right, y equals 0. All right, so how about if we start off with this form, the general form or our polynomial form for a quadratic function, and I want to convert it to the vertex form. How am I going to do that? Well, it's really handy. We actually have a formula to find our vertex in terms of the letters A, B, and C. Just like the quadratic formula solves any quadratic formula set equal to 0 in terms of A, B, and C. It solves for your solutions of that equation by just knowing the values for A, B, and C. So if you want to find H, which is the x value of your vertex, it's the opposite of B over 2A. Now that should sound familiar to you. Does it sound familiar to you, the opposite of B? It's part of your quadratic. And if you're interested, I can show you. Notice if we write our quadratic formula like this, I won't go through the whole thing because I know some of you aren't really interested. But notice that 2A is the common denominator for this and the common denominator for that. So if I separate it out into two terms, this says to find your x-intercepts, you start with your vertex and you go some distance to the right and the same exact distance to the left, because your vertex is midway between your two x-intercepts. Unless you only have one x-intercept, and that happens to be the vertex itself, okay? So when we have real solutions, real number solutions, this is the first part. The negative b over 2a is the x value for your intercept. So if you think you're not good at memorizing stuff, but you know the quadratic formula, this is how you always remember where that opposite of b over 2a comes from. And then to get your y value, you would just plug the x value back into your formula, which is all this says. Take your x value, which is the opposite of b over 2a, plug it in for x, and out pops y. So let's take this quadratic function in polynomial form and let's change it into this form here where we know the vertex. So what can I do immediately when I look at this? What do I know already of the vertex form? The vertex form is going to look like this. Without doing any work at all, what can I plug in right now? Yeah, Bridget? A. Right, so in this form, A is -1. That's the leading coefficient. It means I can put a -1 right here. Just like that, I can do it. So here, A is equal to -1. So here, A is going to be -1. What does that tell me about my vertex? I mean, my parabola. It's pointing downward or opening downward, right? So I know that this parabola is going, my vertex is going to be a maximum value. It's going to be the top of a mountain and it's going to open up downward. So what is the vertex of the parabola? So to do that, you need to know what A and B are. So you go to your polynomial form and you identify A as -1 and B as 4. And you say, okay, H is equal to the opposite of b over 2a. So the opposite of b is -4. 2 times -1 is -2. And -4 divided by -2 is 2. So I automatically know that the x value of my vertex, which we call h, sometimes I like to do this, x with a little subscript of v, just to identify what h is. It's the x value of my vertex, the x value of my vertex. All right, now how do I get my y value? I take this number 2 and I plug it back into my function. I find f of 2. So I have to find f of 2 by plugging 2 in. Now be careful, because this little dash is outside of x squared. That's outside. X is 2. It's not -2 squared. It's the opposite of 2 squared. Plus 4 times 2 plus 1. Question? Oh, you already did it. Okay, -4 plus 8 plus 1 is 5. So our vertex is 2, 5. So let's go 2 and up 5. So there's our vertex. We know 5 is the maximum value that this function takes on. It's the maximum value. It occurs at 2, but I don't really care. 5 is the maximum value because everything else is going to drop. All my other y values will drop from here. Okay, so write the quadratic function in standard form. So we can do that now. F of x equals a times x minus h quantity squared plus k. Now, believe it or not, what do students forget when they do this? They forget the 2. They get so excited about finding h and k and a, and they forget to square it. So you just have a straight line. So make a little note not to forget the 2. So a is -1. X, take away h, which is 2, quantity square plus 5. So this is exactly the same function as this. It's just in a different form. Okay. All right, we know the parabola opens downward because a is negative, a is less than 0. So it opens down. And now to graph any quadratic, you need to find your y-intercept and your x-intercept or x-intercepts, depending on how many you have. And if they're not real, you don't have any x-intercepts that are real numbers. They're complex. Okay, so let's see. Find the y-intercept. To find the y-intercept, I think where the y-intercept is in my mind, I visualize a point on my y-axis, which makes x equals 0. So I take my function and I find f of 0 by plugging 0 in. So I have -1 times 0 minus 2, the whole thing squared plus 5. -1 times -2 squared plus 5, which is -4 plus 5, which is 1. So at 0, 1, I have another point on my parabola. So 0, 1 is my y-intercept. I can automatically get another point right now that's symmetric to my y-intercept. How am I going to do that? Where's my point? If I'm at 0, 1, and my line of symmetry goes right down through x equals 2 as my line of symmetry, where's the other point on my parabola that's to the right of the to the line of symmetry that's at the same height at 4, 1? Because here's my line of symmetry. Let's do that in a different color. My line of symmetry is going right down through x equals 2. My y-intercept is 2 steps to the left, and I'm at a height of 1 unit above the x-axis. So by symmetry, if I go 2 steps to the right, I'm at the height of 1 unit. So I automatically, for free, get another point that's symmetric to the y-intercept, and that point is 4, 1. So you get 2 points right away once you find your y-intercept. Okay, So the last thing we need to know to kind of get a quick sketch of this parabola is to simply figure out where the heck am I going to come down and cross my x-axis. And you can see it's going to be at two different places. And to do that, we set our equation equal to 0, and we find the values for x that make y 0, and use our quadratic formula to do that. I'm going to use this form up here. It doesn't matter. Maybe I should use this one for you, but I'm going to go on the next page because I need a little space. 0 equals minus x squared plus 4x plus 1. So in polynomial form, it's already set up for you. Okay, if you had this form, you would automatically use your quadratic formula. So you would say x is going to equal the opposite of b plus or minus b squared minus 4 times a times c all over 2 times a. So x equals negative 4 plus or minus the square root of 16 plus 4 over negative 2. This is negative 4 plus or minus the square root of 20 all over negative 2. And this is the same as negative 4 plus or minus 2 square roots of 5 all over negative 2, which is 2 plus or minus the square root of 5. Okay, so that's if we have the polynomial form. What do we have? We have the standard form or the vertex form, which looks like this. Okay, so if you're trying to solve that in that form, remember we've got to come up with exactly the same answer. You have a choice depending on how comfortable you feel with this form. You can work with this form as it is, or you can square this binomial, change every single sign, add 5, and come back to this form. Come back to your polynomial form and use your quadratic formula. Because we have a tendency to make a mistake when it's in this form. So let's talk about it and point out where we make mistakes, and hopefully so we can eradicate them. So if I were trying to solve this equation for x, the first thing I would do is get rid of this plus 5 by subtracting 5 from both sides. So far, nothing that's going to cause any problems. I want to solve for x, so I got to get rid of this coefficient here. I divide both sides by negative 1, and I get a 5 here, and I get x minus 2, the quantity square. And this is where we can run into a little trouble. Because when you take the square root of both sides, you've got to remember it's plus and minus. So if you square root both sides, you've got to remember two answers, two x-intercepts. There's got to be a positive and negative there. You add 2 to both sides. Voila, you have your two x-intercepts. They happen to be irrational numbers. So the best thing you can do for graphing is to find out approximately what these two x-intercepts are. And for that, you would need your calculator. So you take out your calculator. I don't need it to be that big. Let's go here and we say, let's find the value of 2, take away the square root of 5. And that's negative 0.23 approximately. 2, 4, doesn't matter. I can't get that close on the scale I have anyway. And 2 plus the square root of 5 is 4.23, 24 approximately. So now I go back to my graph and I put in my two x-intercepts right there, and I just drop my graph and I'm all done. Again, remember, it's just a quick sketch. All right. So well, that was pretty quick. Not quick at all? Oh, well, sorry. The sketch was quick once I found my answers. All right, so I purposely, Caitlin and I purposely chose something that didn't come out so nice and easy. I don't want you to think that x-intercepts are always integers. And sometimes they come out to be irrational and you just get an estimate for them, okay? So let's see, the last thing I want to do is I want to work backwards from the graph to the equation. So let's review something really quick. If I told you that you had a straight line that had a slope of 3, and I asked you to get the equation for the line, what would you need in order to fill out the rest of that equation? What would you need in order to find B if you didn't have the graph with the point, Eli? Yeah, suppose you didn't have the graph and you didn't know where it went through the y-axis. What would you need? I'd need at least a point on the line, right? If I had a point on the line, what would I do? I'd throw it in for y and x, and I'd solve for b. So if I told you it went through like -1, 2, you would put 2 in for y and -1 in for x, and voila, you would have b as 5. And you'd be cool, all right? You'd be all set. That never changes. Even if your polynomial gets more complicated, finding the equation doesn't get any different than that strategy. Once you get every part of your equation except for one of those letters, A, B, or C, you can find the one that's missing by taking a point that's from your graph. All right. So right now, if we use the vertex or the standard form, we can plug in 2 of these values right now. What 2 values can we plug in just from looking at the graph? Josh? You can plug in the vertex. This is H, and that's K. So right now, I go up here and I say, okay, I know what H is. H is 3. And K is 5. There we go, 3, 5. Okay, notice I kept my operations of subtraction and addition absolutely the same from the original form because neither of my coordinates were negative. If either one of them are negative, then if it's my x part of my vertex, that will change to an addition. If it's the y value, that plus will change to subtraction. Okay, but they're both positive, so no worries. All right. Now, I'm almost there. I have to find A. What's the only thing you know about A right now? It's positive. Okay, you know something more about A? I hear someone say it's between 2 numbers? Between 4 and 6 for A. How did you come up with that, Colin? I'm curious. Yeah? So you're saying the value for A is between 4 and 6? What were you thinking of? Okay, all right. Because I was going to say, maybe you know something I hadn't thought of, and it would be great. Okay. So, all right. So it will help you remember what we did with straight lines if you change that f of x to a y. And that's going to help you go back to thinking about the straight line and saying, if our little birdie came down and told me a point on this parabola, I think Mackenzie's the one that said it, I could just plug it right into this formula. Anytime I see a point that has a 0 in it, I like to use it because it makes solving the equation much easier. You could use that point or you could use this point. It does not matter. So where I see x, I'm going to put a 0, and where I see y, I'm going to put a 23, and that's going to allow me to solve for A, which is going to make me very happy because then I have everything I need to solve, to write this equation for the parabola, this function. So 18, I subtract 5 from both sides, and A is equal to 2. So now I look at my instructions, give both forms a standard in the polynomial. Well, my standard form looks like this. 2 times x minus 3, don't forget the square, plus 5. That's my standard form. And to get my polynomial, I have to do the algebra route here to make this into all adding and subtracting polynomial form. But guess what? I actually know 2 of these letters right now. I know 2 of the letters, A, B, or C. Can anybody? Oh, come on, Alex, you're ruining all the fun. Yeah, You know A, because A is the same as the A is here. A is 2. And how do you know C? Yeah, you do have the y-intercept right there, 23. So that way, when you do your arithmetic or your algebra out here, you can make sure that you have a 2 for A and a 23 for C as a little check. So in order to go from your standard form to your polynomial, you have to square your binomial, which is x, the quantity x minus 3. So it's going to look like this, x squared minus 6x plus 9. You have to double every single term, so you get 2x squared minus 12x plus 18. And don't forget to bring that plus 5 down. Students sometimes forget that. And now you combine these two like terms, and voila, you have your polynomial form. A checks, your intercept checks, and you have just found the value for B. Oops, that should have a 1 there, minus 12x. Okay, so this is all you need to know to work on your activities today. If you have any questions, just let me know.